welcome everyone. Welcome and good evening. I'm Brian McGregor. I'm one of the Vice Principals and currently head of the College of Physical Sciences. I'm the chair for the evening as opposed to the speaker or the person who's going to introduce the speaker. So welcome to the university and welcome to the latest R.V. Jones Distinguished Lecture in Engineering. This, I'm told, is the 6th lecture in the series named in the honour of Professor Reginald Victor Jones, or as RV as he's more widely known. R.V. Jones was one of the UK's most distinguished scientists, and he was the head of natural philosophy at Aberdeen from 1946 to 1981. And he's probably best known for his work coordinating scientific intelligence during the Second World War. So this series brings distinguished engineers to the university to talk about their work, and we're delighted tonight to welcome Professor Houlsby as our latest speaker, of whom more in a moment. I have two things now to do. One is some housekeeping issues, and the other is to introduce the person who's going to introduce the lecturer. So some housekeeping issues. First, I've just checked that my mobile phone is on silent. Could everyone else do the same thing or turn it off, please? Secondly, we have no fire drills planned. So if there is a fire alarm, it's real. The exits are clearly signed. Don't panic. The lecture is going to last for 40 to 45 minutes. And after that, we'll have about 20 minutes available for questions. So feel free to think up your questions in the course of the lecture, and you'll have an opportunity to ask them at the end. And finally, in terms of housekeeping, there's a drinks reception afterwards in the James Mackay Hall, which is just out there, and you are all most warmly invited to that reception. So now it's my privilege to introduce the Senior Vice Principal of the University, Professor Steve Logan, who will introduce this evening's speaker. Thank you, everyone.
Colleagues, ladies and gentlemen, I'd like to echo Professor McGregor's welcome to you this evening, where it's my pleasure as Senior Vice Principal to introduce tonight's speaker, Professor Guy Houlsby, Professor of Civil Engineering at Oxford University. As you know, and we know all too well here in Aberdeen, the UK is surrounded by waters with some of the highest tidal velocities and tidal ranges in the world. And this places us in an exceptionally favourable position to exploit the tides for the generation of electricity. Tonight, in this latest lecture in the university's R.V. Jones lecture series, we're fortunate to welcome Professor Houlsby, who is an expert on tidal power and who, in his lecture, will explore some of the ways that we can understand the tides and discuss the potential, the potential energy that can be extracted from this resource. Professor Houlsby is a graduate of Cambridge University and moved in 1980 to Oxford, where he has been Professor of Civil Engineering since 1991 and is currently the head of the Department of Engineering Science. His main research interest was for many years in geotechnical engineering, and he's an internationally recognised expert on offshore foundations. He's also carried out extensive work in theoretical soil mechanics and plasticity theory. More recently, he's developed a particular interest in renewable energy and has a rapidly expanding research group working on tidal power. He regularly lectures in the UK and abroad and has acted as a specialist consultant in civil, geotechnical and offshore engineering on many projects. He's director of a University of Oxford spin-out company, Kepler Energy Limited, which is developing a tidal power system using a novel transverse horizontal axis water turbine. Professor Houlsby is a distinguished academician. He's a fellow of the Institute of Civil Engineers and of the Royal Academy of Engineering, and we're delighted to welcome such an eminent scholar to Aberdeen this evening. Professor Houlsby.
Good evening. Thanks very much for the kind introduction, and thank you all for coming. It's a real pleasure for me to come here and talk about what I regard as my hobby, which is working on tidal power, because as has just been mentioned, really most of my career I've been a geotechnical engineer, so this is a subject I've come to relatively recently. Before I start, I should say that I first heard of R.V. Jones when I was a schoolboy, and my physics teacher was a great fan of R.V. Jones and would regale us with various stories of his achievements. So I find it rather nice to come here and give a lecture in his honour. What I'd like to do is first of all start a little bit with the motivation of why we should be interested in tidal power, then talk about understanding the tidal resources around the UK, and from that then move on to the possible technologies that we could use. And then finally, I'm going to talk a little bit about the context, the broader context of other marine renewables. It may seem the wrong way round to put the context at the end rather than at the beginning, but what I'd really like to do is get the tidal bit out the way first, and then talk a little bit at the end about where the tidal industry sits with respect to the other offshore industries. Okay, so the motivation. Why should we be interested in renewable energy? And really, there are two drivers which we must be careful not to confuse. One is the driver of climate change, and the other is security of our energy supply. So, first of all, climate change. This is a plot which is now known as the Keeling curve, after the person who first plotted it. It's the plot of the concentration of atmospheric CO2 plotted with time for now just over 50 years. And you can see that 50 years ago, the concentration was something over 300 parts per million. And now it's something like 390. These are averaged figures for each year. It oscillates during the year. In 2009 was the first month where the average was over 390 parts per million. It's pretty certain that May 2014 will be the first month with an average concentration over 400. And what you can see on the curve is that not only is atmospheric CO2 going up, but the slope of the curve is steeper now than it was 50 years ago. In fact, it's almost twice as steep. So the cause of this is absolutely clear, although one reads all sorts of nonsense in the popular press. It's our overuse of fossil fuels, our reliance on fossil fuels that is causing this, with all sorts of further consequences. It would be easy to give a whole lecture on climate change, a whole series of lectures on climate change. But the other driver is to diversify our supplies of power. So here's the plot of UK oil and gas production. Oil is the red dots, gas is the blue dots. The scales are very different, but essentially what you can see is that oil and gas production peaked in about 1999, 2000. Of course, most of this comes from the North Sea, not all of it, but mostly from the North Sea. And you can see there's been a pretty steady decline since. We're now down to less than half the peak. That decline will continue. Not quite in a straight line. If you extrapolated the straight line, we'd run out of oil by about 2020. In fact, production is going to gradually slow down. It'll last a bit longer than that, but at a tiny fraction of what it was 10 years ago. We have run out of North Sea oil, and that's just repeated worldwide. The world as a whole is going to run out of oil and gas in about 60 years' time, order of magnitude. You can argue how many decades, but it's decades, not centuries. So we want to diversify sources of energy. And one thing we might look at is the tides. So this is a plot of the magnitude of the main component of the tide. That's the part of the tide that's driven by the moon. And the red areas are where the tidal range is highest. And what you can see is that there are various hot spots around the world. And in particular, one of the main ones is around the UK. Broadly speaking, you can see that they occur on the east and west sides of North America, as I say, around the UK, and some other interesting locations around New Zealand, Australia, one or two sites there. Now, the scale here is such that the maximum value here is only about 150 centimetres. So, in fact, even these hotspots represent only a modest tidal range. What is hidden there is the fact that there are further effects close to the coastline which further amplify the tides. And in particular, around the UK, there are various mechanisms which mean that we get much higher tides than the average in the Atlantic Ocean nearby. And the tidal system is extremely complex. It's not simply the matter of the moon pulling the water around the Earth. It's a very complicated resonance system, and you can think of it that effectively the water is sloshing back and forth in the North Atlantic, and it happens that we get this rather large wave around the UK. So why should we then go to tidal power? Well, first of all, it's entirely predictable. As long as you know where the moon is, you know when it'll be high tide. Tidal power is predictable, unlike wind power, unlike wave power. There are, of course, other predictable renewable resources like solar power. Most of the renewable resources are intermittent. Some are predictable, some aren't. As I've just said, there are good resources around the UK, but also we have a lot of expertise in the UK on exploiting marine resources. There is a marine industry in the UK, and of course a lot of that is based here in Aberdeen, so we're well placed. Well, why not? It is intermittent. The tides are not flowing all the time, and so you can't generate electricity simply on demand. But equally well, solar power doesn't work very well at night, but that doesn't mean to say that one shouldn't try and exploit it. It may or may not be expensive. At the moment, it is looking as if tidal power is likely to be quite expensive. But the price will probably come down as we exploit it more. Now, there are two main ways you can exploit tidal power. One is by exploiting the change in height of the water during the tides, and that leads to things like barrage-type developments, and I think everybody's probably heard of the proposed Severn barrage, which has been sort of on and off the agenda for at least 100 years. But the other possibility is tidal stream power, where rather than exploiting the rise and fall of the tide, you're exploiting the velocity of the water as it flows around the coast. And I'm going to talk entirely about tidal stream, not about barrages at all. So where are the good locations around the UK to exploit tidal stream? So this is a map taken from an atlas produced by the DTI of velocities around the UK at peak tidal flow. And broadly speaking, the yellow areas are areas where the maximum velocity is more than 2 meters a second. And roughly speaking, that's enough to make it economically worthwhile to exploit those areas. So you can see there are a number of different places. One of them, of course, is the Bristol Channel area, which one could exploit the velocities as well as exploiting the depth. There are other sites, for instance, you can see just to the north of Anglesey, there's a good area there, and also south of the Isle of Wight. Now, why do we get these high velocities in various different places? Some are due to the flow around headlands. So, for instance, the northwest and southwest corners of Wales, where the water flows around a headland there, we get high velocities. Sometimes it's where there's an estuary, as in the Severn estuary. And then the other case that's important is where you get an accelerated flow through a narrow channel between two bodies of land. The most famous of those is the Pentland Firth between Scotland and the Orkneys. And by comparison with the rest of this map, the Pentland Firth is completely off the scale because the typical maximum velocities there are about 4 meters a second rather than 2 meters a second. And because of that, everybody is very excited about going to the Pentland Firth for tidal power. And I'll come back to that in a minute. So I'd first like to talk a little bit more about how we can understand tidal power so that we can make rational decisions about how we could exploit it. And in order to understand the physics of tidal flows, you have to understand the flow at many, many different scales. So if we start at the smallest scale, if you're designing a device to extract power from the tides, you'll need some blades in a turbine. You've got to be able to design the appropriate blades. Typically, they might be a few meters long, about, say, a meter across and some fraction of a meter deep. So you've got to be able to analyze the fluid flows on the scale of something like half a meter to a few meters. And then you put these blades together in some device. A lot of the devices look a bit like sort of underwater windmills, and the devices themselves are of a scale up to, say, 20 meters or so. So you need to understand the larger scale flows as they go through the device. But you're not going to get much power out of one device. You need a whole farm of these devices, and the way you arrange those will affect the amount of power that you can get out. So at the next stage up, you've got to be able to look at a whole assembly of a number of different devices. Now, if you like, up to this scale, I could have been talking equally well about wind power, that there you also have to look at the blades up to a whole wind farm. But really for wind, you don't have to look at any larger scale, because at a larger scale, wind farms are pretty well independent of each other. That's not true of tidal power. If you put a tidal farm in one bit of the waters around the UK, that will actually affect the flows in other places. So we've got to move up to the next scale of looking at a whole basin. For instance, looking at all the flows around the Pentland Firth area. And then finally, we need to look at the whole region around the UK to look at interactions between different parts. Now, I'll just give you a few examples from these different scales of analysis to show you the sorts of things that people are currently doing to try to understand tidal power. And in particular, I'm going to be drawing on personal experience and experience from my research group. So let's start at the small scale. I won't go right down to blade scale, but looking at devices, what one's interested in here is looking at the physics of how the flow goes through the device, the interaction between the blades of the turbine and any supporting structure, and trying to understand how the performance of the device will be affected by real conditions. In the real sea, there will be turbulent conditions, there'll be waves. Each of these will affect the performance in some way. And there are modern techniques of computational fluid dynamics, which we can use to study these flows. I'm just going to give you a couple of examples. So the first one is we're trying to answer the question, do ducted turbines work? So for instance, on the left there you can see a proposed design of a turbine in which there's a duct which is channeling the flow through the blades of the device. And the intention is that by accelerating the flow through the device, the expectation is that you would be able to extract more power. And so we've carried out some analyses. On the right here you can see a plot of some of the results of the analysis there. And the question we're asking is it worth going to the expense of this large duct around the blades to accelerate the flow? And if I can just point, I wonder, is there a laser pointer handy here? I can see the chap at the back is about to produce a laser point for me. Sorry, at this stage I really do need to point out one or two things. Great, thanks. Yeah. So don't worry about this rather complicated looking graph. The important part of it is how far to the right each of these curves comes. Now, this plot here is for an ideal, if you like, perfect turbine. I won't go into the details of what we mean by that, but something under completely perfect conditions. This corresponds to the maximum possible power that you could get out. And this curve here is the plot that we get for this particular ducted turbine. So what you can see is we get something like 60% of the maximum power that we could get out from an ideal device. By comparison, this dot here represents the peak in the curve that you get from a device which doesn't have a duct. So the answer is quite clear that putting this duct around the outside is a waste of money. Might not be popular with certain people who are trying to market that device. Here's another device that is currently being tested in Orkney, and this device has a hole in the middle, and one or two manufacturers are suggesting it might be a good idea to have a hole in the middle. So we've analysed cases where you put a hole in the middle. And here's the same plot that we had before. Here's the perfect device. So this would be the best performance we could get. Here's the device without a hole in the middle. And here's what happens as we begin to put a hole in the middle, and you get less power out. Well, that wasn't a great surprise to me. If you put a hole in the middle of the device, you don't get as much power. But that's the device that's being tested. So I do think it's worth doing some of these studies perhaps before proposing some of the devices that are being tested. Let's just move up a scale. Suppose now that you had decided that you could install a certain number of devices at a site and you wanted to know how you were going to lay them out. So we've carried out studies here. The flow is coming through in this direction, and here you can see 4 turbines, here spaced with a reasonable gap in between, here much closer together. How much power do we get out for each case? Here's a plot of the flow. The red part of the flow is where it's been slowed down as it comes to the turbine. Here you can see the 4 turbines close together. Here they're more spaced out. And again, there's a measure of the power that you can extract. If the turbines are widely spaced, that measure comes to about 0.69. Closer together, it's 0.74. We get more power out the closer we put the turbines. So there's a very firm message that comes through that you do better by packing the turbines close together. So that's the sort of study we can do at the next stage up. Now, when it gets really interesting is when we get up to the large scale. So I'd just like to show you some results from some analysis of the Pentland Firth. So the region that we include in the analysis, we have to extend quite a long way out, because if you start blocking the Pentland Firth with tidal devices, then perhaps the water decides to flow round the north of the Orkneys rather than going through the Pentland Firth. So we need to include a large region in the analysis. I won't go into any details of the mathematics of how this is analysed, but essentially it's a computational method. So here's a detail of the Pentland Firth. So here are the Orkney Islands, here's the north of Scotland, and what we've looked at is the possibility of putting lines of turbines across different parts of the Pentland Firth. And first of all, we'll just look at putting one barrier, if you like, all the way across at one location, and then various other possible locations. And if you put a line of turbines across at the first location, that's location A, here, right the way across, you could do various things to the flow of the Pentland Firth. First of all, you could have very few turbines, which would hardly affect the flow at all, and so the proportional decrease in flow through the Pentland Firth would be quite small. And in that case, you find that the extracted power is quite small. And then you could put more and more turbines in, and you would get more and more power out, until you'd reach a stage that you'd put so many turbines in that you'd stop the flow going through the Pentland Firth. And at that stage, because there wouldn't be any flow going through, you wouldn't extract any power. So there reaches a stage where you start reducing the amount of power as you put in more turbines. And the peak occurs here when you reduce the flow velocity through the Firth by about 40%, 45%. Roughly speaking, halving the velocity through the Pentland Firth. And at that stage, the amount of power that we can extract is just under 4 gigawatts. Now, we've studied other possible locations for putting turbines in. So the maximum power, if we go for location A, is just under 4 gigawatts. That's about 3,700 megawatts of power. Just to put that in context, 4 gigawatts is about 10% of the average consumption of electricity in the UK. So as an absolute maximum, we could extract from the Pentland Firth about 10% of the electrical power we need for the UK. Then we can look at what happens if we put turbines at each of these locations B, C, or D. And these are the figures that we get. And then we can look at what happens if we do B and C together, and we get this amount of power. Now, if we compare this number with doing each of B and C separately, we find that we do better because we've done both. So we actually win an extra about 12% by doing these two together, and it's because having blocked one of the channels, blocking the channel next to it is helping, if you like, to achieve more power from the first one. And for instance, if we block at B, C, and D, effectively go across the Firth here, we get almost exactly the same power out as if we go across at A. So it doesn't matter where you put the turbines, as long as you cut off the flow right across the Pentland Firth, you get this same 4 gigawatts out. So there's a fairly important message here. There is a certain total amount of power there, and if you like, you can't extract the power here and then extract the same power again a bit further downstream. If you try and do A and B, C, D, you just get exactly the same as B, C, and D by itself. So you have to understand the interactions between the different possible locations. Now, we've carried out a similar analysis for the Anglesey site, which is slightly more complicated because unlike the Pentland Firth, where you can simply cut across the whole of the flow, the Anglesey site, if you like, has an open boundary on the outside because it's a flow around a headland rather than between two pieces of land. But that shows the analysis on the large scale. Coming down to a bit of detail, here's the flow just around the northwest tip of Anglesey. The turbines are in here. The blue colour indicates lower velocity, where the flow has been slowed down by the turbines, and the red, higher velocity as the flow diverts around the outside. And we've looked at the possibility of a series of rows of turbines, and again looked at the possibility of what happens if you try and put them upstream and downstream from each other or next to each other. And the message that comes out is that essentially if you try and extract power from this line and also from another line that's downstream, you can't get the sum of the two lots of power. If you like, you've used up the power in one location, you can't extract it again at the second. Whereas if you put two devices next to each other, so location A1 and location A2, if you put each of those in separately and then look at what happens if you put them both in together, you do rather better because, if you like, those two locations are helping each other by blocking the flow in parallel. So we're gradually learning about how to lay out turbines to exploit the flow as best we can. Okay, I'd like to move on now to the technology for tidal stream power. And in particular, I'll tell you a little bit about the device that we're developing in Oxford. So, first of all, what are the devices available? A lot of the devices that people are talking about look rather like underwater windmills. These are what are called axial flow turbines, and that means that the axis of rotation of the turbine is in the same direction as the flow of the water. So this is a device being developed by a company called Marine Current Turbines. It looks very much like an underwater windmill. We've already seen these variants with a duct around the outside or with a hole in the middle. There are other variants which involve more complicated ways of anchoring the turbine to the seabed. But there's a whole family of devices which essentially are like underwater windmills. And that's a perfectly sensible group of devices. But there are other options. Some people are looking at vertical axis turbines. So in this case, the axis of the turbine is at right angles to the flow, but vertically. I'll come back later to this option of having a horizontal axis turbine, but at right angles to the flow. And then there are other devices, some that flap up and down. This is being developed by a company called Houlsby Tidal, and that's particularly aimed at extracting power from very shallow flows. And it's a rather complicated device, but seems to me to be quite a sensible design. And frankly, there are then the weird and wonderful devices. This is a thing called tidal sails. And the idea is that you have a series of sort of sails which are launched across the tidal flow to extract energy from it. And a lot of these other devices, I think, are sufficiently weird and wonderful that the chances of them actually working is pretty slim. What I'd like to talk about a bit more is this horizontal axis turbine and, if you like, why we're interested in this. And the reasoning goes as follows. If you want to build an offshore wind turbine, about 10 years or so ago, you would have been building a 2 megawatt turbine. If you're building an offshore wind turbine now, you're probably interested in a 5 megawatt turbine. And essentially, the bigger the turbine you can make, the more power you get out of it, the more economically viable it is. And that's the big driver towards going to bigger and bigger turbines. And there's plenty of room, you can make the turbines bigger and bigger. If you have a tidal device, which looks a bit like a windmill, and you want a bigger tidal device, the problem is you can't just make it bigger because there's a limited depth of water within which you can operate. So what you really want is something that you can make bigger, but you can only stretch it in the horizontal direction. You can't stretch it in the vertical direction. And that's what led us to the idea of a transverse axis turbine. So in this diagram, if you like, the flow goes in or out of the slide. So it rotates about, the device rotates about an axis that's at right angles to the flow. And this is in fact a variant of a well-known type of turbine which has been used in the wind industry for many years, a device called the Darius turbine, but with a few modifications to cope with the rather different conditions that we have in tidal flows. So the idea is that you'd have a device that you could stretch across the flow, make it as long as you like across the flow, and it doesn't matter which direction the tide is coming in, the device always rotates the same way, and you can extract power from it from either the ebb or the flow of the tide. So we've patented this particular device and are currently working towards commercial exploitation of it. And I can tell you now just a little bit about the work that we've been doing to prove that the device actually works. So first of all, we tested a small model of the device in a testing tank at Newcastle University. We didn't have a big enough testing tank at Oxford, so we hired the tank at Newcastle. And the first set of testing we did was simply to prove that the device would actually generate power. So we put it in the tank where we can generate a a tidal flow, and we measure the power that we get out from the device. And we get curves like this. So this is a plot of how much power we get out as a function of how fast the turbine is rotating. So if the turbine is rotating very slowly, you don't get much power out. Gradually the power increases, but again, if you try to rotate the turbine too fast, again the power decreases, because if you like, the drag on the blades reduces the amount of power that you can actually usefully extract. And so there is an optimum speed to run the turbine at, and each of these curves corresponds to a different flow velocity of the water past the turbine. Now, there's a very interesting result here, which when we first observed it with a model turbine, in fact, when the research student was doing this, and he gave me the numbers that came out, I said, don't be silly, go back and do the experiment again, because it must be wrong, because there's a well-known limit here, which is called the Betz limit, which is a theoretical limit that tells you the maximum amount of power that you can extract from a turbine in a flow. And we were getting significantly more than the Betz limit. And so there had to be something wrong with the results. So how many people know about the Betz limit? Oh, there's a few. I claim to be the only person who's managed to get the Betz limit into the letters pages of the Daily Telegraph. Betz limit's a very important thing. Betz limit is to do with wind turbines. So I'll not go through the details of the diagram, but it's a calculation that goes back to the 1920s. If you have a wind turbine, there's a certain amount of kinetic energy that flows through the area of the turbine. The air has kinetic energy by virtue of the fact that it's moving, and there is a flux of kinetic energy through the turbine. And if you want to extract energy from the air going through the turbine, you have to slow the air down by the turbine, and you would think that the amount of power that you could extract would be all the kinetic energy that would be originally flowing through the turbine. The trouble is, if you remove all the kinetic energy from the air, the only way you can do that is bring the air completely to a standstill. And if you bring the air to a standstill, it can't get out the back. So there's some sort of compromise, and the compromise is that you've got to slow down the air just enough that you're extracting the energy from it, but not so much that it doesn't get out the back. And essentially that's the calculation that Betz did. And the result is that you can actually get 16/27ths of the original amount of power that was going through the turbine. That's the maximum amount you can extract. So this limit here is 16/27ths, 59% of the original power going through. And we seem to be able to get a lot more. So what's going on? And we realized actually that the Betz calculation is wrong for tidal turbines for two reasons. And again, I won't go into the detail. One is that it's for air in which there's lots of space for the air to divert around the turbine. And it's not like that in the tidal case because there's a limited depth. And the second thing is that water is heavy and air isn't. And what is very important is the position of the water surface and the fact that you can extract energy from the change of elevation of the water surface. And we've gone back and reanalyzed the problem, properly accounting for that. And when you do that, you can exceed the Betz limit. So if you like, one of the advantages of tidal devices is that they can extract more power than wind devices. I'm going to skip over that one. Now, if you're an engineer, what you're very much concerned about is actually devising a device that will actually be able to withstand the forces that it's subjected to when it's extracting power. So we also did some approximate calculations to work out what the forces would be on the blades in this device. And we did this with an approximate computational fluid dynamics calculation. Again, here's the flow is coming from this side to this side. The blue is the area where the flow has been slowed down by the turbine, and the red is accelerated flow where the water's diverted around the outside. And the result of this analysis was that we could get a plot of where the forces were on the blades as they go round it in the turbine. And again, without going into the detail, we were able to predict what those forces would be. And so the next stage of our testing was to test a larger device with this multi-bay device. You can see these angled blades, and just here you can see some strain gauges. Here's a detail which were used to measure the forces on the device. So we carried out more tests at Newcastle University. Here's the Betz limit again, and with this larger device, you can see that we're now reliably exceeding that, and we were happier about these results because by now we were really believing them. We also measured the forces. So here's the device, which you can just see, I hope, in motion. So you can just see the flow coming through the flume here. Here's the device, and on the end here is the instrumentation that's picking up the loads on the blades in the device. And here's another view of the same thing from above. So you can see the flow is coming down this way. The device rotates about an axis at right angles to the flow. And I said we'd made some predictions of the forces that there would be on the blades, and they vary as the blade goes round each cycle of the turbine. And the prediction that we had was that the forces would have this pattern here, slightly complicated pattern, with a maximum force in one direction at one point of the cycle, and then this slightly curious pattern and a maximum force in the other direction, another point in the cycle, and the measured forces were following a remarkably similar pattern. So at that stage, we were pretty confident that we understood what the forces would be on the device. And this is a very important part of the engineering process, if you like, to be able to have a calculation that tells you what you expect, but to verify that with measurements. And that gives us confidence that we can then use the calculation at full scale. I may say that since then, a different research group, not my own research group, has done some more complicated calculations, and I think these are really rather nice. So these are calculations for our device, but here you can see the vortices that are being shed off the blades as they come round. And CFD stands for computational fluid dynamics, but some people also say that CFD stands for colourful fluid dynamics, and this is a nice example of colourful fluid dynamics. So it's a group at Bath University that have been getting those results. Okay, I'd now like just to spend a last few minutes putting tidal in the context of the other marine renewables. And there are several other sorts of marine renewable. the offshore wind and wave are the ones I'm going to talk about, which are of interest in the UK. I'll just remind you again that tidal does divide into tidal range and tidal stream, and I've only talked about tidal stream. In other parts of the world, they are also talking about other ways of exploiting the marine environment for energy. In places that have got very deep water, there are interesting possibilities of exploiting either salinity gradient or thermal gradient, but there aren't really suitable sites around the UK for that. And there's also the possibility of growing algae and then converting that to biofuel. But I'd just like to say a little bit about wind and wave. And first of all, about wind. Why offshore wind? First of all, the wind speeds are higher the further you go offshore. Secondly, the wind speeds are steadier the further you go offshore, and that's advantageous for wind turbines. So the UK wind industry began with various relatively small developments around quite close to the coast, but in the latest round of licensing of sites for offshore wind, which is now the third round, the sites that are being talked about are much further offshore in regions where there are higher wind velocities. So I'm afraid the colour scheme is not very good on this one, but you can see there are now these much larger sites that are being proposed offshore, including some interesting sites off Scotland. So currently, and every time I give a talk on this subject, I have to revise these figures because they're going up very fast. 19 sites have been developed, 971 turbines, installed power of over 3 gigawatts. The UK has more offshore wind turbines than the whole of the rest of the world combined. It's one of the few industries where we absolutely lead the world. There are almost as many turbines under construction as there are currently offshore. And we're talking about something like maybe 6,000 turbines with an installed power of about 30 gigawatts within the next sort of 15 years or so. So this is potentially a huge industry for the UK. And as you can imagine, with interesting sites not too far from here, there could be a lot of interest in Aberdeen. The standard device that's installed these days is a 5 megawatt turbine. This is actually an onshore 5 megawatt turbine, just to give you an idea of the scale. The rotor diameter of a 5 megawatt turbine is 124 meters, and for comparison, that is a standard international football pitch. So these are very big structures. Another comparison, that is an Airbus A380, the largest commercial airliner. So these are enormous devices, very big, very interesting engineering. Because of the time, I'm going to skip one or two things. The early devices, the early wind turbines, the smaller ones, tend to be on fairly simple structures. One of the interesting things now is that as the turbines are getting bigger and bigger and going further offshore, they have to be put on much more substantial structures. And these are the two experimental turbines at the Beatrice field, not far north of here. And what you can see is that the foundations for those, the substructures, look much more like small oil rigs. And in fact, there's going to be a lot of crossover from the oil industry into the offshore wind industry as the turbines get bigger and bigger. So I think this is a very interesting possibility for future industrial developments. Finally, let me just say a little bit about wave. If you go to if you do some research, in other words, go to Google and look up wave power, you find at least 50 different weird and wonderful devices that people are promoting to extract energy from the waves. And unlike the tidal devices, which you can sort of put into a reasonable set of categories, you know, there are some that look like underwater windmills, there are some that are turbines that are rotating about a different axis, etc. The wave power devices are all sorts of weird and wonderful devices. Now, as I say, there are at least 50 that are being promoted. I am absolutely convinced that at least 49 are not going to work. They mostly look like devices that have been invented by people who really quite clearly do not have any experience of working in the offshore environment, which is very aggressive, very difficult environment. I think, if you like, the 50th that just might work is this one. I'm trying to get the video to work, but for some, here we are. So this is the Pelamis device, which has been tested and is being tested off Orkney. It's a very clever device in that the way it extracts power is by this snake-like structure flexing, and in the joints between the different components is some quite complicated hydraulics to extract power from the process as it flexes. The clever thing about this device is that if you're concerned with tidal power, as I am, the maximum tidal flow that you get is really quite predictable. If you're concerned with wave power, it's very different. If you go to a site where on a typical reasonably breezy day you'll get waves sort of 3 or 4 meters high, something like you saw there, then in storm conditions you'll get absolute monster waves. And making a device that can survive those monsters is really difficult. The clever thing about Pelamis is it's designed so that when the really big waves come, rather than riding over it, it dives through. And so it's the only one of the wave devices that I can see that as part of its fundamental design can cope with the really big waves. And I think that's why I see it as the one that has real potential. So I think wave will come a bit later. If you like, wind power is already quite well developed. Tidal is going to come soon, but wave we've got to wait a little bit further. But it is very exciting because the amount of power available is enormous. So before I stop, I just need to acknowledge the team that are working with me in Oxford, and also some of our major sponsors. We have a lot of other sponsors as well, but those are the major ones. So where are we? I think tidal power is interesting. When you come down to the detail, it looks as if tidal stream could provide about 6% of the UK's electricity. It's not a magic bullet that's going to solve the problem, but it's a useful contribution. What we have to do to get it to work is develop efficient and robust devices, and we've got to understand where to put them in the sea to get best use of the resource. I've just talked briefly about offshore wind. Can certainly provide 20% of our electricity. We already have over 3 gigawatts installed and could have 10 times as much as that. And wave, we're in early stages. So if you like, we're already at the stage that we've got lots of these offshore. I'm hoping that invisible underneath the water in due course we'll have some of these as well. So thank you very much.
we have about 15 minutes for questions. Anyone would like to start? Is anyone upstairs? You probably need to raise your hand rather than press the button in front of you, or just raise your hand generally if anyone would like a question.
So one is regarding these structures that you said, and the industry and the environment, sea environment, because you are using it at sea, and the effect of the seawater on these structures and the maintenance of them, and possibly I have seen the tankers, big tankers, being washed out. If all the system be washed out, and if you can import electricity from sun energy from other countries, much cheaper, 1/3, 1/4 price, is it worth it?
Sorry, I didn't quite catch.
First of all, is you use this device in the marine environment.
Yep.
So effect of the seawater on the all this plant, which is after 6 months, because it's stationary. Because I've seen a lot of effect of the seawater on the structures, and then the maintenance of them, and the cost of the maintenance, and also efficiency due to time, because effect of the seawater on the all the parts of the structure. And also, if suddenly some environmental at sea wash everything out, and the country will be without power, is it worth it to develop this? Because if you can import cheaper electricity from places like Middle East.
Okay, working in the marine environment is difficult. You know, it's a tough environment, and you have to understand issues like the loading on the structures, corrosion, etc. But the UK has a lot of good experience on that, mainly drawn from the oil and gas industry. There's a lot that we can transfer from the oil and gas industry. There are certain things that we can't. The main difference is that effectively the oil and gas industry can throw a lot of money at a small number of big structures. The renewables industry is different. What you need is a much larger number of smaller structures. And so it's got to become much more a production type exercise. But nevertheless, you can use the experience from oil and gas. As an alternative, yes, of course we can get power from overseas. We can import gas from Russia. We could import solar power from Libya. That would be a good place to put solar power. But that's not necessarily securing our power supply.
Well, if you ask them nicely, not with the bombs. Is a way to talk about this. And if you, nuclear issues, if you don't talk and causing trouble for the other nations, and the West, and causing all of problems in the world, and then you destroy the whole structure of the social of the whole world, and this is what is the problem.
I think you've made your point. I think we'll move on to questions associated with the talk. If you want to pursue any of these issues, I'm sure.
Yeah, as a marine officer, I know that any structure at the sea,
if we could move on now, please. Okay. We'll take some other questions. Anyone else? So let's see. One here, and we'll take one up there.
Is it on?
I'm taking a couple down first.
Oh, sorry.
There were a couple here, and then I'll come up to you in a moment. Gentleman here, the gentleman here.
Yeah, hopefully a simpler question. When you talk about 6% and 20%, could you just clarify what you mean by that? Because, are you assuming this is when at peak tidal flow, is all these devices are happening at the same time? Could you just sort of clarify how you get to those numbers?
If you like, when I say 6% and 20%, what I mean is a real 6% and a real 20%. So that is accounting for the fact that the tides are intermittent, you taking into account the capacity factor, etc. So it's the average output compared to the average electricity requirement. So for instance, the average consumption of electricity in the UK is about 43 gigawatts. It's a useful number to bear in mind. Every person in the UK, on average, consumes about 3/4 of a kilowatt. You know, of course, it's very irregular summer and winter. So the installed power in the UK is about 90 gigawatts to cope with the fact that of the fluctuations in demand. When I talked about 30 gigawatts potentially installed wind power, that's the total installed power, but of course the wind doesn't blow all the time, so the average power that you get from that 30 gigawatts installed is about 8 gigawatts. And you know, it does annoy me when one reads in the papers that, oh, the wind's not blowing today, I've noticed these windmills aren't going round, what a waste of time. You know, believe it or not, people do not spend millions and millions of pounds on building wind farms without working out the fact that the wind doesn't blow all the time. You know, they have actually worked that out. So, you know, about 30 gigawatts installed would be about 8 gigawatts average output. That 8 is about 20% of the 43. So, and tidal power about a third of that, but accounting for all the variations through the cycles.
Gentlemen.
Hello. Will your turbine be relevant for shallower flows, rivers, tidal basins, ordinary hydro?
Yes, it would, but if you like, if potentially you could have an ordinary hydro scheme, you would do better with your ordinary hydro. There are... it's actually for the same reason that if you're at a location where you could put a barrage, you get more power out with a barrage than with a free stream type turbine. It's to do with if you have a free stream turbine, you can extract a certain amount of power that is useful power that you get, but inevitably there's also some wasted power because of mixing processes that happen downstream of the turbine. And you can avoid those mixing losses with a barrage type concept, or with, if you like, ordinary hydro. So if you were at a site where you could do ordinary hydro, you'd be better doing that.
Okay, gentleman upstairs.
Hi, Peter Meenan from Atkins Energy. I'd just like to thank Professor Houlsby for an excellent presentation. A couple of questions, if I may. I'm very intrigued by the logic of the horizontal axis turbine, the Darius type rotor. In our experience with axial turbines, it's quite advantageous to be able to have pitch adjustment on the blades. It would appear to be difficult with horizontal axis turbines. Have you any observations? And a second question, if I may, the notion that we can eventually get 30 gigawatts of capacity, what are the implications for base load to match that? Thanks.
Yeah, first of all, you can have variable pitch cross-flow turbines, but you're right, it's quite complicated to arrange. So the device that we're looking at is deliberately fixed pitch, but you can still get reasonable power out of that. In fact, the main advantage, if you could go to variable pitch, would be that you could reduce the section of the turbine blades. But as the size of the blades is partly driven by strength considerations anyway, that wouldn't be a big win. So we're quite content with sticking with fixed pitch, although it does have some drawbacks, I'll admit that. But we think there's more of an advantage just to have a device with minimum number of moving parts. The second question was about the integration. If we had 30 gigawatts of wind power, how would we integrate that into the grid as far as baseline power is concerned? I'm not an expert on grid integration, and there are a lot of people who are very expert in that area. It's an extremely interesting control problem, and as an amateur in that area, my understanding is that at the moment, the way the grid operates is to a large extent, we treat the demand that comes from domestic users and industry, etc. We treat that demand as something that just happens. And then we try to satisfy that demand by base load and then switching on various different devices. So there are some devices on the grid that can respond very quickly. For instance, the pump storage schemes like Cruachan, for instance, which effectively what Cruachan does is boils kettles in Glasgow, at the right time of day. So you pump lots of water uphill, and then everybody comes home, puts the kettle on, Cruachan drains out, and that's the way you cope with that demand. There's tremendous scope in the future, I think, for manipulating demand as well as supply. And things like smart metering, which will be coming in, so that, you could have a washing machine that would be effectively monitoring the price of electricity, and your washing machine would know that it had to get the washing done sometime in the next 24 hours, but only turn itself on when the price of electricity dropped below a certain value. And so there are all sorts of possibilities of evening out demand. So I think as we get more renewables on the grid, there's a lot of complicated things need to be done to integrate the renewables into the system, and part of that is manipulating demand as well as manipulating supply. It's a really interesting area. Almost makes me wish I was an electrical engineer. Not quite.
I think we've perhaps got time for one last question. Can I see if there's two here. Let me see if there's any upstairs, because people upstairs tend to get neglected. Is there any from upstairs? Nope. Okay, let's take these two here. The gentleman here first.
I was just wondering, at the start of your talk, you asked us to think about security of supply, but not cost. Could you comment on where cost would fit in your vision here?
Yeah, as potential, commercial developer in this area, we're acutely aware of cost. Cost is a function of time. I mean, the costs at the moment would be high, but the cost of, for instance, offshore wind is coming down. I think one of the few certainties in the whole of this business is that the cost of oil and gas is going to go up continuously with time, and the cost of renewables is going to come down because of increased experience. And so for me, it's only a question of when do they cross over. At the moment, oil and gas, particularly gas, are much cheaper sources of power, but it's not going to be like that forever. And really, we should be preparing well in advance of when those costs cross over. I'm sure renewables will be economically viable in due course.
Okay, thanks for this.
Your turbine is completely submerged. Is there any benefit building a device that's only partially submerged? I mean, what's the benefit of, rather than paddle steamer blades in the water? Would that work?
You could do. I've never really thought of a device which wouldn't be. I mean, paddle steamer blades are actually they're quite inefficient, because there are essentially two types of devices that you can have of turbine types. There are what are called lift devices and drag devices. And if you like, the paddle steamer type blades are drag devices. Drag devices inherently work at lower speeds with higher forces. And the lift devices are working at higher speeds and smaller forces. And so, if you like, although they're more complicated to understand, the lift devices are more favourable from an engineering point of view. I can't think why there might be an advantage in not being submerged all the time.
Let me just check. This will have to be the last one, I'm afraid. Gentlemen.
Very simple question, probably quite a difficult answer. But how soon do you think your tidal flow device would perhaps be commercially viable? Technically viable rather than commercially, perhaps?
It's technically viable now. How long will it take to get it, a prototype into the water and actually generating power? If we have something in the water in 4 years' time, I'd be very happy. I think the limiting factor is not to do with the engineering, it's to do with, to a certain extent, the financing, but to a greater extent, permissions. We have a very rigorous but rather slow permissions process in the UK.
Yeah, it mirrors what it is with wind as well, I think.
Okay, I'm afraid we'll have to call a halt now. My thanks to everyone for coming. The constant flow of questions suggests that you've all enjoyed yourselves. So could I ask you to thank the speaker in the normal way? Thank you, everyone. And if a reminder is needed, there are drinks outside as you go out, so please enjoy yourself. Thank you.